Welcome to the glass plate. In today's example, we're going to take a look at a bucket that you filled with water up to a height of 30 centimeters, but there is a small hole through which water is leaking. That hole is at a height of a centimeter above the bottom, and it has a diameter of 4 millimeters. You have tapped 5 liters of water in this bucket. And we would like to know, okay, you've done so at the tap, you needed water somewhere else, so you're going to walk to somewhere else, but you're losing water. How long can you walk before all your water is gone? We're going to do that here by an estimate. We're going to estimate how much water you lose just after filling, so when the water level is high. And we're going to assume that that is a constant amount of water that's flowing out, and then you can easily back out how long it takes before all water is gone. That is obviously only an estimate, because when the water level drops, this outflow will going to drop as well. But we won't be concerned with that for the moment. We're going to try and estimate how high this velocity here is in this opening that I call point 2, and I'm going to compare that to what happens here at the free surface that I call point 1. Once I know V2, I can back out with the size of the hole how much water flows out, and thus equate how long it roughly takes before the bucket is empty. But we need to get a grip on V2. And for that we're going to set up a steady Bernoulli equation. So I'm going to compare point 1 and 2, and I'm going to say everything that happens for a droplet from moving here to there is that it started with a certain amount of energy, and it will still have that energy. I'm going to ignore the frictional effects, which are rather small in these cases. So what I've written down, that mechanical forms of energy at the top are still there, but reshuffled at this small hole where it flows out. And now I need to see what is important. The pressure here is the atmospheric pressure P0, sitting at top. The pressure here, there's a jet flowing out that is also surrounded by air, thus at the pressure of the surroundings. And those pressure effects go out. Then I'm left with velocities. The heights I do know. Here is a small height of a centimeter, here is a large height of 30 centimeters. What can I tell about the velocities? I need V2. What about V1? Well, a mass balance tells me that in steady state, what flows in must flow out. So I look at the velocity here, at the flow rate here, and there. So in minus out. And kind of have this just below that surface as my control volume. There is inflow here, there is outflow there. That inflow is the flow of that coming down of the free surface level. And this has that velocity V1 in it, and the area of the bucket times V1 times the density gives me the flow that's coming down. And that is the same as what goes out, the area of the hole times V2. And obviously the area of the bucket is much larger than the area of the hole, and thus what I find that V1 is much smaller than V2. Okay, but here that is even squared. So V1 squared is much smaller than V squared 2, and I can ignore this one compared to that one. Now I have an equation for V2. If you read what is left over here, we have that the velocity in the hole V2 equals square root out of 2g, the difference in height between the surface and the position of the hole. And if I compute that, I have 2.4 meters a second. Then I can turn this into a flow rate, a volume flow rate, area of the hole times V2, and I can turn that into a mass flow rate by multiplying this by the density, or I can just use that VV and say, okay, how long does it take before everything is gone? That's the original volume equals then the amount that's going out per unit time times time. And it gives me an estimate of about 3 minutes before the bucket is empty. Okay, summing up, simple Bernoulli idea that energy here and energy there must be the same tells me that I can back out a relation between velocity and the height. The velocity I could find because the velocity at the surface is much, much smaller than the velocity here, so it starts virtually with zero kinetic energy compared to what it gets, and thus I see that the velocity is only a function, by and large, of the height difference, and from that I could compute time. What should I do if I want to do better? Well, you can see that clearly here. I have put in here the constant number 30 centimeters to find all these numbers. But this is not a constant. This will change. And that changing can be tracked by setting up a mass balance in which you equate how much that volume is coming down. And that volume contains that h, and thus I get something like the ddt rho A of the bucket times h equals what flows out is minus rho phi sub v, that is this outflow, and that is the area of the hole times the velocity in that hole, and that is a dynamic equation. So that should be coupled here, and now you see that you get a differential equation. The h dt is proportional to the square root of h minus small h. If you work that out, you will find, sure, the outflow gets smaller and smaller, and it takes longer and longer to empty another part of the bucket. And if you do that, you will find that the emptying time is quite a bit longer. I leave that up to you for a rainy Sunday afternoon. Good luck.